We continue with the invariant subspaces and characteristic polynomials and the direct sums of subspaces. Okay, so we start with we start to continue more precisely the proof of the theorem 524. Let me recall where we are at this point. So this is theorem 524. Okay, let me switch the color. Okay, so we have the following theorem. So assume T is a linear operator on V, where V is a finite dimensional vector space. Okay, and suppose that V is given by the direct sum of its subspaces W1, W2, etc. through WK. Okay, where we have that Wi is a T invariant subspace for each I. Okay, so for each I between 1 and k. Okay, so this is the situation. We're given a bunch of invariant subspaces, so that the whole space is the direct sum of them. All right, and in this situation, we can calculate the characteristic polynomial of T in terms of the characteristic polynomials of its restrictions to the subspaces Wi. So namely, let us denote but by Fi of T, the characteristic polynomial of T restricted to Wi. All right. Then we have that the characteristic polynomial of the whole linear operator T is just the product of the characteristic polynomials for Twi. Okay, so just the product of F1 of T times F2 of T times etc. times Fk of T. Okay, and of course we know that a product of polynomials is a polynomial. Yeah, so at least at this level the statement makes sense, and we are going to finish the proof today. All right, so let me recall where we stopped last time. So we have established the base case. Well, okay, so first of all, for k equals 1, this is trivial, right? Because we simply, in that case, we simply have the W1 is equal to V. And so T restricted to W1 is just T itself, because we are not restricting to any proper subspace, right? So of course, then we have that F of T is just, let's call the characteristic polynomial F of T here, okay? So F of T is going to be the characteristic polynomial of T. So in this case, we have that, of course, F of T is equal to F1 of T. So this is the case k equals 1, nothing to prove here. Okay, so the first non-trivial case, and in fact, this case already contains most of the complexity of the general k, is the case k equals 2. And this is what we did last time. Okay, so we proved for k equals 2 last time. So proved last time. All right, so now we're going to show that this is also holds for an arbitrary k, arguing inductively. Okay, so the inductive step, starting with k equals 2. Okay, inductive step. So assume that the theorem is valid for k minus 1 greater or equal than 2. Okay, and we will prove it for k. All right, so we're going to prove it for k, starting with k equal to 3. All right, so let's show this. The idea is to use the case k equal 2. So we want to split the case for k into two parts. Somehow we want to use the case k minus 1, and we want to use the case 2. Okay, so the idea is to split into these two. So, okay, so let's just see what we have. So we are arguing now for k, okay, trying to prove the theorem for k. So suppose we are given that V is the direct sum of W1 through WK okay, where each one is in particular T invariant, right? So with each Wi a T invariant subspace. Okay, so we have K subspaces. So let's try to use the inductive part, which tells us that the theorem is true for K minus 1. Okay, so for this, let's look at the first K minus 1 subspaces. So let us write W to denote the sum of the subspaces W1 plus W2, etc., plus WK minus 1. Okay, so I'm skipping the last one. So I only take the sum of the first K minus 1 of my subspaces. Okay, then we have that W is a T invariant subspace of V. Okay, so let's make sure, let's check it. So assume that X belongs to it. So X belongs to W, which is the sum W1 through WK minus 1, right? Okay. So let's remember what it means for a vector to belong to the sum of subspaces. So this means that X can be written as a sum of some vectors, X1 plus X2, etc., plus XK minus 1, right? For Xi in Wi, right? So we have this for some Xi's, right? Okay, but then if we want to calculate T of X, so of course T is linear, right? So we can write this is the same as T of X1 plus etc. plus T of Xk minus 1, right? So by linearity of T. And we know, since each Wi is T invariant, right? So we have that T of Xi still belongs to Wi as each Wi is T invariant, right? So we have that T of X still belongs to the sum of these subspaces, W1 plus WK minus 1, right? Because again, by the previous line, T of X is written as the sum of vectors T of X1, TXK minus 1, for which we know that this belongs to W1, this belongs to WK minus 1, right? So this means that this still belongs to the sum, and the sum is equal to W, okay? So we just use linearity of T to conclude that the sum of the first K minus 1 subspaces is itself a T invariant subspace, all right? So we have this for W, okay? All right, so then we also have that V can be written as the direct sum of W and WK, okay? So we need to check this, okay? But the claim is that V is the direct sum of W and WK. All right, so let's check. So this follows from the assumption. So indeed, first of all, we have that V is equal to the sum of W plus WK, right? So this we have, you all agree? So this we have simply because we knew that V was the, because remember what is W basically, yeah? Because W is W1 plus WK minus 1. And we know that V is the sum, well, moreover, even the direct sum of W1 through WK. Okay, so we have that this is the sum. Now we need to check that it is a direct sum. So we have these conditions on the intersections, okay? And if we have that X belongs to W intersected with WK, okay, so assume this happens, we want to show that then X is 0, right? So then we have that X belongs to the sum of Wj over J not equal to K, right? Intersection with WK. But this has to be the zero vector space because we know by assumption that V is the direct sum of W1 through WK, right? So this is so it follows that any intersection like this must be trivial, and so we conclude that then this X has to be zero, so this intersection is trivial as well. So this tells us to go back for a second. Oh, let me just copy. Okay, so again, so we conclude that V is the direct sum of W and WK. Okay, but look, now we only have it as a direct sum of two spaces, right? So we can apply the case K equals 2, which we proved previously. So by the case K equals 2, we get that the characteristic polynomial of T, so Ft, okay, can be written as the product G of T times, let's say, Fk of T, okay, so where G of T is the characteristic polynomial of T restricted to W, right? So this is just the case of the theorem applied for K equals 2, which we already know. All right, but now we can use the inductive assumption, right? Because look, G of T is the characteristic polynomial of T restricted to W. But let's remember what W is, right? So we have that W is the direct sum of W1 through WK minus 1, excuse me, right? Is everyone okay with this? So remember, we took W to be just the sum, okay? We defined W to be simply the sum, but in fact, then it's automatically going to be the direct sum because all of V was the direct sum of the spaces. So the conditions on the intersections can be easily checked. So check the conditions of the form, let's say Wi intersected with the sum overall I from 1 to J, excuse me, from 1 to K minus 1. And so that J is not I, Wi equals 0. So the fact that this is empty follows because if we can intersect it even with the bigger set and still get 0, right? Because look, this part, so I guess I'm checking this myself, right? Okay, so because this part is of course a subset of the sum J equals 1 to K for J not equal to I. Wj, and here should be Wj as well in the previous line. You see? So from knowing that the whole space was the direct sum, it follows in particular that W is also the direct sum of the first K minus 1 subspaces. All right? Okay, but then now we can use induction for W, right? Hence, we have that G of T, the characteristic polynomial of T restricted to W, here, G of T, is the product, right? So it's going to be equal to F1 of T times etc. times Fk minus 1 of T, right? By the induction hypothesis. Okay, but then we conclude that F of T is the product, right? So it was the product of G of T times Fk of T, which is then equal to F1 of T times F2 of T, etc., times Fk of T. So this gives the desired conclusion. Okay, so let me pause for a minute. You can have a look. We did this check. Okay, so right. So we have this. So this tells us the theorem, right? So that we can calculate the characteristic polynomial as a product of the restrictions. Well, the characteristic polynomials of the restrictions of T to a bunch of T invariant subspaces like this. So we can get immediately corollary for diagonalizable operators. So let's switch to a new page. Okay, so I'm going to prove a corollary. So suppose that T is a linear operator on V. As usual, V has finite dimension, and we assume that T is diagonalizable. Okay, so assume that T is a diagonalizable linear operator, and let lambda 1 through lambda k, let's say, be its distinct eigenvalues of T, of course. Yeah, the distinct eigenvalues of T. Well, of T. Okay, so we already know that the whole space is then the direct sum of the eigenspaces, right? This was something we proved in the previous lecture. So by theorem 511, proved in the last lecture, we have that V is a direct sum of the eigenspaces of T. Right? So we know this holds when it's diagonalizable. Note that each eigenspace is in particular T invariant. So this is something again we remarked earlier, right? That eigenspaces are invariant always. So this means we can apply this theorem we just proved. So we can apply theorem 524 that we just proved to this situation in the hope to understand the characteristic polynomial, right? So sorry, I should have been clearer. So the point of this corollary is to actually give you a recipe for how to calculate the characteristic polynomial of a diagonalizable linear operator very quickly. I mean, we kind of know it already, but let's see how the theorem immediately implies it. So each eigenspace is T invariant. So we can apply the theorem, okay? So for each eigenvalue lambda I, we consider T restricted to the eigenspace corresponding to this eigenvalue, E lambda I, okay? And let gamma I be an ordered basis for this eigenspace, so for E lambda I, okay? So everything is finite dimensional, so let's denote these dimensions by mi. So let the dimension of E lambda I be equal to mi, okay? And then we can write the the basis gamma I as some vectors v1 through vmi, okay? So let's write it like this. So then for each j between 1 and mi, we can quickly see that applying T restricted to the subspace to Vj, well, since it's a vector in the eigenspace, it's, T acting on it corresponds to just multiplying by lambda I, right? So this is just lambda I times Vj, okay? And so the point is that if we now look at T E lambda I of Vj, and I look at the coordinate vector of this with respect to gamma I, what do we get? So we get zeros everywhere except for the j's position, right? So we get 0, 0. In the j's position, we just have lambda I, and after that, we have zeros again. So this is going to be the coordinate vector, where lambda I is the value in the jth column, jth row or jth position, okay, of this vector. Okay, so we know these vectors. So we can write the matrix which represents T E lambda I with respect to gamma I, right? So we know this again pretty much. So it's follows that the matrix is going to be very simple form. So it just has lambda I everywhere on the diagonal, lambda I, and zeros outside of the diagonal. Now, what are the dimensions? So let's make sure we understand the dimensions. So the dimensions correspond to mi, the dimension of the eigenspace E lambda I, right? So this is an mi by mi matrix. So this is mi, many columns, and mi many rows. Okay. So the matrix has this very simple form for the restricted operator, restricted to E lambda I. Okay. So we can calculate the characteristic polynomial very easily. So the characteristic polynomial of t restricted to E lambda I, right, is by definition the determinant of this matrix. So T E lambda I with respect to gamma I minus the variable T times the identity matrix, the mi by mi identity matrix, right? Okay, but in this case, it's a diagonal matrix. So what we get is just lambda I minus T to the power mi, right? The product of the diagonal entries of this. All right, so this gives us the characteristic polynomial of T restricted to E lambda I. And now we can use the theorem 524, which tells us that the characteristic polynomial of T itself is just the product of this over all eigenspaces, right? So we get that the characteristic polynomial f of t of t itself. So, okay, the usual, but let me just make sure. So f of t, the characteristic polynomial of t itself, okay, so it's going to be the product. So we have lambda 1 minus t to the power m1 times, etc., times lambda k minus t to the power mk, right? And this k corresponds to the number of distinct eigenvalues of the operator. Okay, so in particular, we get that the multiplicity, so remark, yeah, the multiplicity of each eigenvalue is equal to the dimension of the corresponding eigenspace. Right? Because remember, the multiplicity means the power with which such a monomial enters the polynomial, the maximal power for which the monomial divides the polynomial. This is algebraic multiplicity. But here we get that this is exactly m1, for example, for lambda 1, and in general mi for lambda I, where mi is the dimension of the eigenspace. Okay? So we have this very nice picture for the case of a diagonalizable operator. Later on, we'll try to understand what happens in more general situations. But before that, as usual, we want to define the corresponding statement and notions for matrices. Okay. So as usual, throughout this course, we are maintaining this duality between spaces and matrices. Sorry, not spaces, I mean linear operators and matrices, okay? So let's just formulate the analogs of what we did for linear operators, also for matrices. So definition, assume we have B1 an M by M matrix over some field of scalars F, and similarly we have B2 an N by N matrix over F, okay? So square matrices, but possibly of different sizes. Okay. Then we define the direct sum of B1 and B2, denoted as B1 plus B2. Again, we use the same symbol, and you'll see why soon. So this is the direct sum of B1 and B2. Okay. This is going to be the m plus n by m plus n matrix. Okay, so still a square matrix, but its dimensions are now the sum of the dimensions of B1 and B2. So this is going to be the m plus n by m plus n matrix A, such that it's defined as follows. So the entries Aij of this new matrix are going to be defined as follows. It's going to be the corresponding entry of B1 if the indices fit into the interval corresponding to B1. So for all ij, so that they are both between 1 and m, okay? Now it's going to be the entry of the matrix B2, but the indices now are going to be I minus m, j minus m for all I and j, which are between m plus 1 and n plus m, and we're going to put zeros otherwise. Okay, so this is the formal definition. We'll see a picture in a second, yeah, to get you a better intuition about this. So if now I have matrices, let's say B1 through Bk, if all of these are square matrices, all over the same field, F, okay, possibly of different sizes. Okay. Then we define the direct sum of these matrices. So we define the direct sum of B1 through Bk, all right? We define it recursively as follows, okay? So we're going to take the sum, the direct sum, B1 plus etc. plus Bk, all right? So this is going to be defined to be the sum of the first k minus 1, k minus 1, and then we take the sum with Bk. Okay? So you see this definition makes sense because first step we define the sum of the direct sum of two matrices. Now we have to define it for any number of matrices. Okay, so we do it recursively. We already have defined it for 2 in the first part here. Now, for example, for 3, so we are going to take the direct sum of the first 2, and then this gives us another matrix, and then we take the sum of this matrix with the third one. So again, we are only adding 2 matrices at a time, right? This way we define the sum for 3, then we define it for 4, for 5, etc. So in general, it's defined using this recursive formula. All right. So now let's draw a picture, which is very simple, yeah? Like if this recursive formula might seem complicated. So if A is the direct sum B1 plus B2, etc. plus Bk, okay, then in fact it is of the form which we can draw as follows. So it's going to consist of k blocks on the diagonal. Okay, so let me draw it like this. So we have B1, B2, etc. Okay, I need one more, sorry. So we have Bk here, right? So we have these blocks on the diagonal, and we have zeros everywhere else. Well, 0, 0. Yeah. So this is simply a matrix. So the direct sum is just a bigger matrix where you take each of the summands, put it on as a block on the diagonal, and so make sure that the total dimension is the sum, the number of rows and the columns is the sum of the numbers of rows and columns in each of the BIs respectively, right? Okay. So you can check that this formal definition that we made here corresponds exactly to defining the matrix like this. Okay. All right. So we have this definition. Okay. So now we formulate theorem 525. And what this result really is just a version of like a matrix analog of the result for that we already have for invariant subspaces. Okay, so let me just formulate it. Let T belong, let T be a linear operator on V. As usual, the dimension of V is smaller than infinity. Assume we have W1 through WK, T invariant subspaces of V, right? Such that the direct sum is all of V. So we have, this is the direct sum of W1 through WK. Okay, so the same setup as we had before. Now, for each I, we fix a basis. Let's call it beta I. Let this be an ordered basis for Wi. All right. And we let beta be the union of those. So this is the union beta 1, union beta 2, etc., union beta k. All right. Now, what do we have in terms of matrices representing all of this? So let us take A to be the matrix representing T with respect to beta. And remember, this makes sense because the union of bases for each of these subspaces gives us a basis for the whole space, right? So note, we already know that beta is a basis for V, right? So it makes sense to talk about the representation of T with respect to beta. Okay, and we can write Bi to be the matrix representing TWI. Well, T restricted to Wi with respect to the corresponding basis beta I for Wi. Okay, so we take this for each I from 1 to k. And then we have the expected result that A is actually the direct sum of the matrices B1 through Bk. Okay. All right. So the matrix can, if we have, we can split our space into a direct sum of subspaces invariant for T. Then the matrix representing T consists of these blocks representing T restricted to the corresponding subspace. Okay. And proof of this is in fact a homework exercise, but as you can see, the idea is to use the result we just proved. Yeah. So to use the earlier result that we proved. So homework. All right. So we have this nice connection between block matrices and the space being is direct sum of invariant subspaces. Right? So we have this, okay? Any questions about this result? Okay. So if not, this actually more or less the final result for now about invariant subspaces. Okay. So this summarizes somehow, this is the main like picture we wanted to conclude from how we can analyze a linear operator by breaking the space into subspaces. And you saw some exercises where this maybe was helpful in the homework. For example, to characterize the, well, in some cases when we want to determine the characteristic polynomial, it simplifies the task. Here we see also for the matrix representation, we have this nice way to calculate the matrix representing T if we know the matrices for the restrictions, for its restrictions to subspaces. Okay, so the moral of all of these arguments is always the same. Like if we're given a linear operator, it might be hard to understand it. So we try to simplify the problem by splitting the space into smaller subspaces. And then we analyze our linear operator on each of them separately, restricted to each of them separately. Some divide and conquer type arguments. Okay. So this kind of it for now for invariant subspaces. So the next thing we are going to bring into the picture is inner products and norms. Okay, so we're going to see how, if there is some way to talk about distances. So of course, this is something you already saw in 115a. And we'll see now how this interacts with this more advanced analysis of linear operators. Okay, so we're going to do again some reminder from 115a that will be needed for further analysis, for our deeper analysis of this decomposition into subspaces. So for this, I need to do a little review of 115a, a couple of things. So the first thing I want to remind you about or to review is inner products and norms. Okay. So I assume you've all seen this, but again, I think it's good to make sure we're on the same page. Okay. So when talking about inner products and norms, we want to restrict the field of scalars to make it either the reals or the complex numbers. Okay, so from now on, f is either R or C. Okay. So I recall the definition of inner products. So let V be a vector space over F. Okay. Then an inner product on V is a function which takes pairs of vectors x and y and sends them to scalars. Okay, so where the scalar corresponding to the pair xy is denoted as this triangle brackets xy. So this is a function like this from v square to f. Okay, and it satisfies a bunch of axioms. So the first one, we have linearity in the coordinates. Okay, so we have x plus z inner product with y is the same as x inner product with y plus z inner product with y. So this holds for all x, y, z vectors in V. The second axiom, be the same for multiplication by scalars. So we have cxy is equal to c times the inner product xy. So this holds for all xy vectors in V and c scalars in F. Okay. Now C, the next axiom, is symmetry or rather conjugate symmetry of this operation. So if we look at xy, the inner product of xy, and I take its complex conjugate, then this is going to be the same as the inner product of yx. Okay. So let me remind you, this is complex conjugate. Okay. And this holds for all xy in V. In particular, if our field of scalars is the field of reals, so if f is R, then you don't need to, it does nothing, right? Complex conjugate. So then we have simply that this function is symmetric. The inner product of xy would be the same as yx over the reals, but in the complex case, we require taking the conjugate. And finally, D. So if you take the inner product of x with itself, it's going to be always greater than 0 as long as x itself is not 0. Okay, so this holds for all x and x. All right, so these are the axioms. So the idea is that these axioms abstract from the definition of, for example, the standard dot product, but also they apply to many other examples. So, but let me mention this example, the most important example, I guess. So the standard inner product on the space Fn, okay, is given by the following formula, and this is the same as for dot products. So for two vectors x, with coordinates, let's say a1 through an, and y with coordinates b1 through bn. Okay. For two vectors like this in Fn, we define the inner product, x inner product y, by taking the sum over all I from 1 to n, and we take the products of the coordinates, ai times bi, okay, but we also take the complex conjugate for bi, if needed. Of the reals, again, we don't have to do it. All right, so this is the standard. Whenever we say standard inner product on Fn, this is what we mean. The same formula as for the dot product. All right. So now let me recall that for matrices, we have this notion of conjugate transpose, which is the same as transpose, but we take complex conjugates as well. Yeah. So for a matrix with m rows and n columns over F, it's conjugate transpose matrix. Sometimes synonymously one uses a joint matrix. So a joint, okay, these are two synonyms in the literature. This is the matrix which we denote as A star. Okay, so let me write here A star, where the entries of this matrix are given by the following formula. So the entry of the matrix A star in the position ij is going to be AJI conjugate transpose. Okay, and we have this formula for all ij. Okay, so this gives then an n by m matrix. Okay, now let's introduce some more terminology. So definition, a vector space V over F, okay, endowed with a specific inner product is called an inner product space. Okay. So whenever we say an inner product space, it means we both have a fixed vector space and a fixed inner product operation on it, right? But of course, there can be many different inner products on the same vector space. So when we say inner product space, it means we already fixed some particular inner product. Okay. Now, if we have that the field of scalars is C, we will call the corresponding inner product space as a complex inner product space. Okay, and if F is the field of reals, we refer in this case to it as the real, as a real inner product space. Okay, so just some terminology to shorthand all these notions. All right. So now we have a theorem from 115a, which summarizes some of the basic properties of inner products. So this was theorem 6.1, which I recall. So let V be an inner product space. Okay, so I will write IPS for brevity. Then for all x, y, z vectors in V and scalars C in F, we have the following simple properties. So first of all, if I take x inner product with y plus z, then I'm going to get x inner product with y plus x inner product with z. So here, of course, we just combine the linearity plus symmetry from the axioms, right, etc. So all these properties are easy. Follow quickly from the axioms. So similarly, we have x inner product with c times y is going to be c complex conjugate times the inner product xy. Similarly, for c, we have x inner product with 0 is the same as 0 inner product with x, and this is just 0 always. We also have that x inner product with itself is 0 if and only if x is equal to 0. And finally, we have that if we have that the inner product of xy is equal to the inner product of xz. So assume that this happens for all x and v and fixed y and z, yeah. Then in fact y has to be equal to z. So if two vectors have the same inner products with all other vectors, then they're already equal. All right, so these are some basic properties of inner products. And finally, whenever we have an inner product on a vector space, we can define a notion of the norm or distance or length, depending on which terminology you prefer. So let me just recall this. So definition: if V is an inner product space, okay, then for X, a vector in V, we define the corresponding norm of this vector. It is denoted with two vertical lines like this, yeah. And we take it to be simply the square root of the inner product of X with itself. Okay, so this is the norm of a vector with respect to a given inner product, to a fixed inner product, yeah. All right, so I'll stop here today. Next time I'll finish by recalling some of the basic properties of these inner products. We'll briefly review the Gram-Schmidt orthogonalization process. So you might want to actually recall it because I won't spend time on this. I will recall it very quickly. If you don't remember the details of how it goes, I encourage you to refresh it for yourself. Okay, the Gram-Schmidt orthogonalization. And yeah, okay. And so after that, after we review all this stuff, we'll go back into this invariant subspaces and this deeper analysis of linear operators in the situation when there is some notion of norm present in the picture. All right. So I'll stop here. Thank you very much for coming. And I'll see you either in the office hours today or on Monday. Okay. Thank you very much.